Okay, let's do another proof. So we've got the same DFA as we had before, the DFA that accepts all strings that ends in zeros. And we want to formally prove that the set of strings that this accepts really is the set of all strings that end in 0, right? So that was our best guess, and it looks like it's legit. But we want to formally prove that, okay? So once again, we have to prove two things. We have to prove if it's in the language, then it's accepted. And we have to prove if it's accepted, then it's in the language. So we'll do the easy case first. And the easy case is usually assume it's in my language, then it's accepted. So we're going to prove W is in curly L implies W is accepted. Okay? So we're going to assume W is in curly L. W is in curly L, that means W ends in a 0. That means there is some string, alpha, such that W can be written as alpha 0. So W equals alpha 0 for some alpha. Okay, so we want to prove that regardless of what alpha is, we want to prove for all alpha, so for all strings alpha, n star of S0, so from the start state, reading alpha followed by 0 ends in a final state. And there is only one final state, so instead of writing an element of f, we can just write it as equal to S1, because there's only the one final state. Okay? Now how do we prove this? We're going to prove it by induction, but it's not immediately clear what we're going to do induction over, because alpha is not parameterized by some n, right? Alpha can just be any string in the world. So what we're going to do induction over, we're going to do induction on the length of alpha, because alpha is a string, it's going to be a finite length. It could be length 0, length 1, length 2, length 3, so we're going to do induction on the length of alpha. Induction on length of alpha. Okay, so let's have a go and see if this works, right? So base case is the length of alpha is equal to 0. Well, the only length 0 string is the empty string, so that basically means alpha is equal to empty. So n star of S0 epsilon 0 is the same as n star of S0 0. S0 reader 0 go to S1. Cool, that checks out. Step case. We're going to assume the property to be true for all strings of length n. So assume true for any string alpha with the length of alpha being equal to n. So we're going to assume for all alpha with the length of alpha is equal to n, we're going to assume that n star of S0, what are we doing? N star of S0 alpha 0 is equal to S1. Okay, so that's the property we're going to assume. And then I want to prove it's true for all strings of length n plus 1. Okay, so we're going to prove for all alpha of length n plus 1 that the property holds. That is, maybe I should choose a different letter. So for all beta of length n plus 1, n star of S0 beta 0 equals S1. Okay? Now if beta is a string of length n plus 1, that means beta is equal to x alpha, where x is a character, i.e. either 0 or 1, and alpha is a string of length 1, string of length n. And that's how we're going to try and like weasel in our inductive hypothesis. So we can replace beta with x alpha 0, where alpha is any string of length n. Oh, not any string, let me rephrase. For any string beta, there is some alpha, such that beta can be written as x alpha for some x. So I guess if I wanted to write that formally, for all strings beta, there exists an x, there exists an alpha, beta is equal to x alpha. So for example, if beta is the string 1, 0, 1, 1, you can choose x to be 1, alpha to be 0, 0, 1, and then clearly beta equals x alpha. So you give me beta, I can always find you a corresponding x and an alpha. So with this property here, we can then do cases on x, right? Because x is either equal to 0 or x is either equal to 1. So we do cases on x. if x is equal to 0, n star s naught 0 alpha 0, I can use the definition of the extended transition function. So that's n s naught 0 alpha 0. If I'm in S0 and I read a 0, I go to S1. This becomes n star of S1 alpha 0. And now it looks like I'm a little bit stuck, right? Because it doesn't look like I can apply my inductive hypothesis here. So it looks like the thing I'm trying to prove is not a strong enough property, right? It looks like I'm going to have to prove something stronger because I can't get from here to S1, right? I'm stuck. So what other properties could I assume? Well, if we look at the DFA, we know that from the start state, if a string ends in a 0, it'll always get to S1. And it looks like it's the case if I'm already in S1 and I'm reading a string that ends in a 0, it looks like I'll still be in S0, right? Because if I'm in S0 and I read a 0, I go back to S1. If I'm in S1 and I read 0, 1, 0, 0, 1, 0, I still go back to S1. So it looks like we might need the property that for any string alpha, if I'm in S1 and I read alpha followed by 0, I stay in S1. So it looks like we might need to do induction on a stronger property, right? So let's try that again. So it looks like we actually need to prove a stronger property than what we want. So we want to prove for all strings alpha, from the starting state, reading alpha 0 is equal to S1, and from the state S1, reading alpha 0 is still S1. Okay, because this proof didn't work, we got stuck. So let's try proving the stronger property instead, which hopefully should work. So, base case. Alpha is so once again, we're doing induction on length of alpha. On the length of alpha, which we denote the length of a string as these absolute values. So the base case is the length of alpha is equal to 0, which is the same as saying alpha is the empty string. N star S naught epsilon 0, well, we already did that case before, we found that was S1. And N star S1 epsilon 0 is the same as N star S1 0. If I'm in S1 and I read a 0, I go back to S1. Okay, cool, that worked. So now we're going to assume two inductive hypotheses. We're going to assume that for all alpha with length of alpha equal to n, that the property holds. So we're going to assume from S0, reading alpha 0 gets me to S1. And we're going to assume from S1, reading alpha 0 also gets me to S1. Okay, and we want to prove for all beta, where the length of beta is equal to n plus 1, we want to prove both of these properties. So we want to prove from S0, reading beta 0 gets me to S1. We want to prove from S1, reading beta 0 gets me to S1. Okay? So just like before, we can use this property here, right? So beta is equal to x, some character x, and some string alpha, where x is equal to 0 or x is equal to 1, and alpha is of length n. Okay, so hopefully this time we can use our inductive hypothesis. So let me just segment this off. So I will try to prove this property first. N star S naught beta 0 is the same as N star S naught X alpha 0. By definition of beta, we can rewrite it as an X and an alpha. Then we've got two cases. So the case for X equals 0 and the case for X equals 1. If X equals 0, this becomes N star S naught 0 alpha 0. Use the definition of the extended transition function. So we can take the 0 off. Okay. If I'm in S naught and I read a 0, I go to S1. S1 alpha 0. And now I can use my inductive hypothesis, right? Because I know if I'm in S1 and I read a string of length n, alpha, followed by 0, I say in S1. Cool. Now let's try the other case. N star S0 1 alpha 0. So by the definition of the extended transition function, from S0, read a 1, and then read the rest of it, alpha 0. If I'm in S0 and I read a 1, I'll go back to S1. So that leads me, so S0, read a 1, go back to S0. So I can replace this term here with S0. And once again, now I can apply my inductive hypothesis, right? Because here alpha is a string of length n, and I know for any string of length n, if I'm in S0 and I read alpha 0, I go to S1. There we go. Both cases hold, so this property is true. Now we've got to prove the other property. So we have to also prove n star of S1 beta 0 is equal to S1. I'll leave that to you as an exercise. The proof is basically the same as this case here with S0s flipped to S1s. So you punch it out, you do cases on X, and then you use inductive hypotheses from both cases to get S1. So I'll leave that for you as an exercise. Okay? And so assuming you've done that, then what have we shown? We've shown that this property here, right? We've shown that if W is in the language, or W is in curly L, then W is accepted, right? S0 W is equal to S1. And how do we do that? Well, we proved a stronger property, right? We proved this property here. I'll put it in a little box. We've proved for strings alpha, if you're in S0, read alpha 0, you get to S1. And if you're in S1, you read alpha 0, you get an S1. So really, I only wanted this property here. But I needed to prove both, otherwise the induction proof wouldn't work. So I've proven this property here. Therefore, I've proven for all strings in the language, this property holds. So the only thing left to do is to do the backwards direction, right? Which we'll do in the next video. So I encourage you to have a go at the backwards direction. You can follow the proof we did last time. We tried to do the contrapositive. So have a go at that, and then we'll do the proof together.